we will begin our 11th lecture today, and I am going to give this lecture the same title as the lecture I gave last time, because it turns out that I did not get to what I wanted the main theme to be. So, I will go back and change the title from last time. So, let us continue the title. So, we will call this the minimum distance of a linear code, right. So, let me just begin with a recap. So, first we made a couple of observations relating to linear algebra. We defined what is meant by the row space. Then I went through the fundamental theorem of linear algebra. After this, we proved that the double dual is the code itself. We next focused on lemmas. We provided two lemmas helpful in finding a parity check matrix H for the code. And then we looked at what it means to talk about a systematic generator matrix. And so, this is for this particular case, we showed how find H in this case. Then we talked about why a systematic generator matrix is of interest in the first place. Why is it of interest to have such matrices? And then finally, towards the end of the lecture, we started talking about when do such matrices exist. So, when do systematic generator matrices exist? Okay. So, this is about where we were, and as I told you, I am going to go back and I want to change the title of our last lecture. So, we will rename it now, and again this is making use of technology. So, let us take advantage of that, and I am going to call this, in hindsight, a systematic generator matrix. Because that turned out to be the focus of our lecture. So, let me save that and get back to today's lecture, which has the title of finding a minimum distance, the minimum distance for linear block code. Now, so just taking a look back again at the last lecture here, towards the end what we actually said was we were faced with the question, does every code possess a systematic generator matrix? And the answer we gave was that if your matrix is k by n, and if the first k columns are a full rank, then there exists a systematic generator matrix. But if not, it's not like the code is hopeless in terms of being systematic, because you can always find some other set of symbols with respect to which the generator matrix is systematic, okay, meaning that you can actually shuffle the columns of the generator matrix and arrange it into a form so that the first k columns are linearly independent, and then that generator matrix would be systematic. However, it would not be a systematic generator matrix for the original code, but rather for one whose coordinates are shuffled. So, because of that, I will just close that topic with this statement. So, perhaps we will just look at the last slide of our last lecture, which said that two codes of block length n are said to be equivalent if there is a map which is 1 to 1 and on to, and which corresponds to a shuffling of the coordinates, okay, or a permutation of the coordinates. All right. So, let us go back here, and so we will conclude that discussion by saying from the discussion in the last lecture, it follows that every linear code C is equivalent to a second linear code C prime, which possesses a systematic generator matrix. Okay. So, that concludes the discussion on that particular topic, and now let us move on to talking about how one would go about computing the minimum distance of linear block code. I will just pull up my tool set that I use here, which is very helpful. So, the minimum distance of a linear block code. And we will begin straight away with a theorem. The minimum distance d min of a linear block code C is equal to the minimum Hamming weight to the minimum Hamming weight W min of a non-zero code word. And the proof so of course let's say that you have a code that contains 10 code words, okay, and then supposing you had to find the minimum distance of the code and you did it in a brute force fashion, and so let's say it was a linear code. What you could do is you could look at all pairs of code words within the code, which would be 10 choose 2, and then you would have to compute 10 choose 2, which is 45 different pairs, and then you would choose the minimum. But with linear codes there is a major simplification. You do not have to do that. You can just simply find it by looking at these 10 code words, or rather 9, because in a linear code word there is always going to be one which is 0. By the way, if you are thinking that how can a linear code have 10 code words, you are absolutely right. A linear code word can only have code words, a number of code words equal to a power of 2. So, let us say there is a linear code with 16 code words, one of them is 0. So, you only have to check the weight of the remaining 15, and the minimum weight will then give you the minimum Hamming distance. So, this is a big simplification which holds only in the case of a linear code. So, let us see how we prove that, and then we will quickly look at some examples. So, proof: let C have Hamming weight C equal to W min. Then that means that the Hamming distance between C and 0 is equal to W min, and so now we found a pair of code words whose distance is W min. So, from this it follows that therefore, the minimum distance of the code must be less than or equal to W min. So, that is the first observation. On the other hand, let C1 and C2 in C be such that dH of C1 C2 is equal to D min. But this implies that the Hamming weight of C1 plus C2 is equal to D min. Why is that? Because the minimum distance, Hamming distance between a pair of code words is precisely equal to the Hamming weight of the sum of the code words. Okay. So, that means that you found, and this belongs to the code, this belongs to C, since C is linear. So, that implies, this implies that W min is less than or equal to D min. So, we have two equations, one which says, and let us call this 1, which says that the minimum distance is less than or equal to the minimum weight, and 2 which gives us the reverse inequality. Therefore, from 1 and 2 we have that D min is equal to W min, and we are done. Okay. So, the minimum weight is equal to the minimum distance. Let us apply that in an example. Supposing we take C to be the repetition code, then we know that C only contains 2 code words, the all 1 code word and the all 0 code word. So, when we compute W min of a code, of course, we must look at the minimum Hamming weight of a non-zero code word. So, from that it follows that therefore, W min is equal to 7 is equal to D min, and we have seen that before, but I just want to illustrate how much easier it is to find the minimum distance if you use this. It is not so clear here, it will become a little clearer in the next and perhaps even more clearer in other examples. Let us look at another example. So, let C be the single parity check code. So, this is so C is precisely the set of all code words having the property that Ci I is equal to 1 to n is equal to 0. So, it is clear from this that if you want the sum of all the symbols to be 0, then there must be at least 2 1s for this to happen. Therefore, W min is equal to 2 is equal to D min. So, we have dealt with our 2 examples. So, the natural question is, well, what about the Hamming code? Wasn't that our third code? Well, it turns out that in the case of a Hamming code, there is an alternative method of finding the minimum distance, and so let us see how we handle the Hamming code. I will take us back to the last lecture where we might actually have okay, let us see if I can find it. It is either in this lecture or the one before that. Here it is. Okay. So, I am going to now I am going to select the page and copy it so that we can use it in our current lecture. So, let us put that down here. So, from an earlier lecture we saw that the matrix that you see here in the middle of your page, this one, is actually a generator matrix for the Hamming code, all right. So, now we also want to use the fact that this generator matrix is in the form of a systematic generator matrix. Okay. So, let me let us remove some of these lines which we do not need. Then we see that this part is the identity and this part is the P, all right. And from that we know that we can actually write down the parity check matrix of the Hamming code. So, perhaps just so that people do not get confused, let me erase all the redundant bits of information on this page, at least redundant for this lecture. Okay, so this eraser is proving to be a little temperamental here, but it's okay. All right, so we have the generator matrix here, and now based on this I can actually put down a parity check matrix for this code, and therefore H is equal to P transpose I n minus k, which in this case turns out to be so I need to take the transpose, I have to change the rows to columns. So, it is 1 1 1 1 0 1. So, 1 1 1 1 0 1 1 1 0 0 1 1 1 1 1 0 0 1 1, and then beyond that we just have the identity matrix, so this is then our parity check matrix for the Hamming code. And now if I look at the parity check equation, so this is H then, which says that Hx is H times C is equal to 0. And if I call these column vectors of the matrix, let us call them, maybe I should choose a different color. So, let me write this in blue, H1, H2, H3 all the way up to H7. Then it follows that H times C equal to 0 if and only if sigma Ci Hi equal to 0, I is equal to 1 to 7. Now, this is an important equation, because what it actually says is that every code word represents a linear dependence relationship amongst the columns of the H matrix. Okay. So, we are interested in finding out the code word that has the minimum Hamming weight and which is non-zero. So, in other words, that is saying, well, what is the smallest set of columns within the parity check matrix of the Hamming code I can find which is dependent. Okay. So, let us go back to the parity check matrix, and I am going to actually remove this red for fear that it will cause confusion. So, here is just the matrix itself, and you notice that there are 7 column vectors. And another thing, so if you were in class, I would have asked you this question: what do you notice about this matrix? Is there anything special about the parity check matrix of the Hamming code? And in fact, the observation that we will make in a second is an observation that will allow us to generalize from this particular Hamming code to the general Hamming code, right. Now, going back to this matrix, you see that all non-zero 3 tuples, there are 2 to the 3 minus 1, which is 7 non-zero 3 tuples, and all of them occur here: 0 0 1, 0 1 0, 0 1 1, 1 0 1, 1 0 1, 1 0 0, 1 0 1, 1 1 0. So, all of them occur precisely once. And if you are looking for the smallest set which is dependent, you know that no 2 are dependent, because all of them are distinct, but certainly it's easy to find examples where 3 of them are dependent, right. So, for example, if you were to add, let's say if you were to add this first column to the second column, right, you would get 0 1 0 and you would find that here. So, what that's telling you is that there is a code word in the Hamming code which has the following symbols, which has a 1 1 0 0 0 1 0. So, you see that you can go directly from a dependence relationship amongst the columns of the H matrix to a code word. So, that means that when so again let me repeat what I had said earlier. If you are interested in finding out a non-zero code word of minimum Hamming weight, that is equivalent to asking the question, what is the smallest size of a dependent set within the columns of a Hamming parity check matrix, and the answer clearly is 3 here. Okay. So, from this point of view, the minimum distance of the Hamming code is 3. So, I will just write this very briefly by saying that d min is equal to 3 for the Hamming code by inspection of the parity check matrix. Okay. You might say, well, that is too brief an explanation, but that is fine, because we will actually explain this in detail later. So, this is in some sense a preview of a general theorem that we will actually prove, which is going to take us to the second method of finding the minimum distance of a linear code. The first method says, well, find the minimum Hamming weight of a non-zero code word. The second method is telling us, look at the columns of the parity check matrix, and from that sometimes it is easy to find the minimum distance, or at least it is feasible. So, for that we need a definition. So, we are going to introduce a parameter S. So, given an n minus k by n parity check matrix of an let us also give this a name. So, for parity check matrix H of an nk linear block code C, we define the parameter S to be the largest integer such that any, and this is important, such that any S columns of H are linearly independent. All right. Now, you might say, wait a minute, I thought you said that the minimum distance was linked to the smallest number of columns that is dependent. Well, that is very closely related, because if you find the largest set which is always linearly independent and you increment that by 1, then you will get the smallest set which is dependent. Okay. And that leads to our next theorem. Theorem d min is equal to S plus 1. It is very simply stated, and the proof is very simple. Follows from the observation that the existence of a code word C of Hamming weight W implies the existence of a linear dependence relation amongst the columns of the parity check matrix H. Okay. So, that is the proof, and let us do one thing just to make the proof clearer. Let us go back and apply it to the Hamming code. So, here is the Hamming code's parity check matrix, and the theorem says that d min is S plus 1. So, all that we need to do is compute S. Now, S is the largest integer such that any S columns of the parity check matrix are linearly independent, and you can see by inspection that any two columns are linearly independent, because they are dependent only if they are the same and none of them are the same. Okay. S cannot be 3 because you can find subsets of 3 columns which are dependent. For example, the first, the second and the sixth are dependent, as we saw earlier, because the sum of the first and the second is precisely the sixth column. All right. So, example, S is equal to 2 in the case of the Hamming code, hence d min equals 3. Now, we have seen that earlier. So, this is an alternative and perhaps the simplest way of actually finding the minimum distance of a Hamming code. And you can actually use this to define a family of codes, and this family is called the family of Hamming codes. So, I will just simply call this the general Hamming code, meaning that the code that we looked at earlier was a specific Hamming code because it had the specific block length 7. So, in general we would have the following definition. Let R greater than or equal to 2 be an integer, and then set set n equal to 2 to the r minus 1. Then a Hamming code of length n is any code possessing a parity check matrix of size r by 2 to the r minus 1 all of whose columns are non-zero and distinct. All right. So, then again going back to the example code here. So, here r, the parameter r is equal to 3. So, the length is 2 to the 3 minus 1, which is 7, and all the columns are distinct. So, if for example, you were to replace r equal to 3 by r equal to 4, then the Hamming code would be defined in terms of a parity check matrix which is a 4 by 15 matrix. Since r is 4, 2 to the r minus 1 is 15. So, it would be a 4 by 15 parity check matrix, and the columns would be all distinct. It does not matter which order, distinct and non-zero, and it does not matter what order you put the columns in, it will still be a Hamming code. Okay. And so, next, so that leads us to the question, what are the parameters of the Hamming code? So, I will just, this does not require a proof. So, clearly it follows that the general Hamming code has parameters n equals 2 to the r minus 1, k equals 2 to the r minus 1 minus r, and d min equal to 3. Okay. So, if this is not clear to you, then I would suggest you work this out, because it is simply a consequence of the nature of the parity check matrix of the Hamming code. Now, this observation about the minimum distance of a code being equal to s plus 1, where s is the largest integer such that any s columns of h are linearly independent, leads to a bound which is called the singleton bound. So, theorem, singleton bound, d min is less than or equal to n minus k plus 1 for any n k code C. And why is that? Well, that's simply because your H, your parity check matrix H, is n minus k by n. So it follows that from the size of H that S cannot be any bigger than n minus k, because you know that the rank of H is less than or equal to n minus k. So from this it follows that d min is at most S plus 1, so it is at most this. So that is the proof, right. Now, and so here is the definition. A code whose d min achieves the singleton bound with equality is called a maximum distance separable code. And that is abbreviated MDS code. Now, the reason for this term is quite clear, because what we are saying is that if a code is MDS, then the minimum distance is as large as possible, which means that in some sense you are trying to keep the code words in the code as far separated as you possibly can. Of course, so that leads to the question, is it possible to construct these maximum distance separable codes? The answer is yes and no. Yes, it is possible, but the codes that you can construct in the binary case are not very interesting. Excuse me. It turns out that in the binary case, the only possible MDS codes are either the repetition code or the single parity check code. There is no other code that is MDS. However, it turns out that if you look at non-binary codes, which we have not studied up to now, that in the case of non-binary codes, it is possible to find MDS codes. In fact, even though we have not talked about these, I am sure many of you have heard of the class of Reed-Solomon codes. So these are the codes that are used which are in widespread use, for example, in compact disks and in deep space communication, for example. These are a well known and very powerful family of non-binary codes which happen to meet the singleton bound with equality, and they are called therefore they are examples of MDS codes. So let us go ahead and see why it is that how it is that the repetition and the single parity check code meet the bound with equality. So example 1. So we will take the repetition code. So in general, so this is, let us say, the general repetition code. So let us say that this is the general repetition code. So this such a code has parameters n, 1, n. So since this is n k d, it means that d min, this is d min of course, is equal to n minus k plus 1. Therefore, it is an MDS code. So, the general repetition code where all the symbols are the same and there are still only 2 code words is an example of an MDS code. Now, similarly, if you look at the example of the general single parity check code, then its parameters are length is n, the dimension is n minus 1, the minimum distance is 2. Simply because if you take a look at the set of all n tuples, there are 2 to the n of them, and half of them are even parity, half of them are odd parity. So, the number is 2 to the n minus 1. So, the dimension is n minus 1, and the minimum distance is still 2 because the minimum Hamming weight of a non-zero vector is still 2. So, here again this is n, this is k, this is d min. So, here again d min is equal to n minus k plus 1, therefore, MDS. And from this you might be tempted to conclude that perhaps it is easy to construct MDS codes, but the fact of the matter is there exist no other classes of binary MDS codes. These are the only possible families of binary MDS codes. And since their minimum distance is either the minimum distance is very small or their dimension is small, these codes are called trivial codes. These two classes of codes are sometimes called trivial codes. Now, trivial does not mean that they are of no use, it just means that from an academic point of view they are not very interesting. Okay. All right. So, that concludes our quick discussion of bounds of the minimum distance of a code and related topics. Now, we will go on to talk about, we will introduce a new topic, which in a way you could view as continuing this theorem. This theorem provided us a bound which relates some of the parameters of linear block code. So, now we are going to give other bounds. Okay. So, bounds on the size of a code. And there are two bounds in particular that we will actually discuss. The first bound is the Hamming bound. And the Hamming bound says that says that the size M of an NMD code C is upper bounded by C less than or equal to 2 to the n times the sum I goes from 0 to t, n choose I, where t is equal to d min minus 1 upon 2 floor. Okay. So, this is what the Hamming code says. Now, so how does one go about proving that? The idea is very simple. By the way, when I say, I guess this notation here is the floor function, which means that t is the largest integer which is less than or equal to d min minus 1 upon 2, and I assume most are familiar with that. So, how do you prove that? The proof proceeds as follows. Let us say that this is an abstract depiction of the set of all n tuples, and there are 2 to the n of them. Okay. So, they are scattered all over in here. Okay. And now, supposing, so let me erase that since I do not want these to show up. Supposing I have 2 code words, supposing I have a code word C1 and I have a code word C2 and I have other code words as well. If I draw a sphere, a Hamming sphere of radius t surrounding each of these 2 code words, then we know from a lemma that we showed early on that these 2 spheres are disjoint. Okay. If C1, C2 are code words, then so I see that we just have about a little over a minute left. So, perhaps I should just quickly summarize, and if you do not have time to finish the proof, I will continue this next time, it is not a problem. Perhaps it is worthwhile summarizing what we looked at today. So, the main goal was to actually show means of actually computing the minimum distance of a code. So, we showed that you can compute it by computing the minimum Hamming weight and then by computing the parameter s and saying d min is s plus 1. That led us to the general Hamming code as well as to the singleton bound and to MDS codes. After that, we began our new topic studying other bounds on codes. We started the Hamming bound and we will continue from that point onwards in the next class. Okay. Thank you.